By looking back in time, we can glimpse the universe's past. But eventually, we reach a point where everything becomes obscured. At that point, light is no longer the key. Hello, everyone. When we gaze at the night sky, we're not just seeing stars, we're looking billions of years into the past. But did you know? Even the most powerful telescopes can't peer beyond a certain limit. That limit is 380,000 years after the Big Bang, the moment when light was first released into space. Before this point, the universe was dense like fog, filled with plasma and charged particles, trapping photons, particles of light, from escaping. The wall of the universe, the cosmic microwave background, CMB. What we call the oldest light is the cosmic microwave background, CMB. A faint thermal glow left over from the moment the universe first became transparent. Everything humanity has ever observed is blocked by this cosmic wall. Before that, everything can only be reconstructed through theory. What we cannot see, but still try to understand. Physicists are chasing clues from the universe's infancy through neutrino background radiation, ghostly ultralight particles released even before photons, evidence of cosmic inflation, found in tiny fluctuations within the CMB primordial gravitational waves, though extremely difficult to measure. However, nothing is certain. All hypotheses about the period from 0 to 380,000 years after the Big Bang are theoretical models and may never be fully verified. But even though we can't see it with our eyes, humanity never stops searching. We simulate, hypothesize, and compare with current observations, step by step, trying to decode the chaotic picture of the universe's earliest moments. So what really happened in those first fleeting instants? Coming up next, we'll step into the Planck era, where every known law of physics completely breaks down. This is the absolute beginning. No space, no time, no physical law can describe this place. Time, 0 to 10 to 43 seconds. Unimaginably small. We call this period the Planck era, the earliest phase of the universe that can be defined in physical terms. It lasted only about 10:44 seconds after the Big Bang. What was happening? We don't know. Not because we lack information, but because all existing physical equations break down at this point. Space and time had no clear structure, no fundamental particles existed, no forces were distinct. Quantum mechanics and general relativity completely contradicted each other. A chaotic quantum soup. During the Planck era, the entire universe was compressed into an incredibly tiny space, a singularity. Here, energy was so dense that even the concepts of before and after became meaningless. Time could not be measured, space could not exist. Everything was just a chaotic field of probability, where the laws of physics were only beginning to emerge. Why Planck? The name comes from Max Planck, the physicist who founded quantum mechanics. Planck time, 5.39 minus 10 to 44 seconds, is the smallest unit of time that modern science can calculate. It also marks the boundary that current cosmological models cannot go beyond. To understand the Planck era, humanity still needs one crucial thing: a theory of everything, a theory that unifies general relativity and quantum mechanics. Theories like string theory, loop quantum gravity, and M theory are all attempts to reach this moment. But so far, none has been definitively proven. The universe began in a blind spot, with no light, no time, and nothing but possibility. But right after the Planck era, everything began to shift, and the first fundamental forces emerged. You've heard of the 4 fundamental forces of nature: gravity, electromagnetism, the strong force, and the weak force. But once upon a time, all of them were one. Time. From 10:43 to 10:36 seconds, right after the Planck era ended, the universe entered a new state, known as the Grand Unification Epoch. At this stage, gravity had already separated and began acting independently. The remaining 3, electromagnetic, strong, and weak, were still unified as a single superforce called the electro-weak-strong force. All particles, all interactions, merged into one. At incredibly high energy levels, around 1029 Kelvin, matter had not yet stabilized into the particles we recognize today. Instead, the universe was a uniform energy field, where particles constantly transformed into one another through quantum processes. The universe at this point resembled a boiling sea of energy, where particles had no distinct identities. Why grand unification? In theoretical physics, scientists believe that at sufficiently high energies, the strong force merged with the electro-weak force, forming a superforce that governed all particles and fields. This is the core idea behind the Grand Unified Theory, GUT, a crucial step toward building a future theory of everything. Which theories describe this era? Since it can't be directly observed, physicists rely on theoretical models such as string theory, quantum field theory, extended standard models, GUT models. But there's a major obstacle. Gravity does not unify with the other forces. This makes the unification of all forces extraordinarily complex. The end of grand unification. As the universe continued to expand and cool, energy levels dropped. Eventually, the strong force broke off from the electro-weak-strong superforce. And at that moment, a universe-changing event began: cosmic inflation. A burst of space expansion occurred at speeds beyond all imagination. In a moment so brief it defies imagination, space itself expanded faster than the speed of light. The universe didn't grow gradually, it exploded into size. Time, from 10 to 36 to 10 to 32 seconds. We're talking about a time span shorter than 1,000 trillion trillionth of a second. Yet in that fleeting instant, the size of the universe increased by at least 1026 times, meaning its volume grew by a factor of around 1078. What actually happened? After the strong force split from the electro-weak force, the universe entered a state of extremely high energy, known as the inflaton field. And in the blink of an eye, this field released an enormous burst of energy, causing space to expand exponentially. The universe, once smaller than an atom, was suddenly inflated to a size larger than 15 light years, all within a million trillion trillionth of a second. Didn't that break Einstein's theory? Not quite. Einstein's relativity forbids matter from moving faster than light, but space itself can expand at any speed. And that's exactly what happened. The theory of inflation solves three key mysteries that the Big Bang alone couldn't explain. Flatness problem. The universe appears nearly flat, not curved. Horizon problem. Regions far apart in the sky look identical, despite never having had time to exchange information. Monopole problem. Magnetic monopoles, hypothetical particles, should exist, but have never been observed. Right after inflation ended, the energy stored in the inflaton field was released as particles, marking the start of a new era. The universe was now large enough to continue expanding at a slower pace. The temperature began to drop. Fundamental forces continued to separate, and that led directly into the electro-weak era, when the first particles began to acquire mass. There was a time when every particle in the universe had no mass. Then a strange quantum field emerged, and everything changed forever. Time, from 10 to 32 to 10 to 12 seconds, right after the universe underwent its colossal inflation, it began to cool rapidly. This marked the beginning of the electro-weak epoch, one of the most pivotal periods in the history of physics. As the universe cooled, forces continued to split. At first, the electromagnetic and weak nuclear forces were still united as a single force, the electro-weak force. But as the temperature dropped to around 1015 Kelvin, the two forces separated into electromagnetism, governs light, electricity, and magnetism. Weak nuclear force, responsible for nuclear decay, such as beta decay. This is when the Higgs field came into play. Before this moment, particles like quarks, electrons, and the W and Z bosons were all massless. But with the emergence of the Higgs field, these particles began to interact with it and gained mass. Imagine a room filled with fog. The more a particle interacts with the fog of the Higgs field, the more it gets dragged down, and this interaction creates mass. W and Z bosons, carriers of the weak force, very massive, decay quickly. Higgs boson, the final proof of the mass-giving mechanism, discovered in 2012 at CERN. These particles aren't just crucial to particle physics. They define the very structure of matter in the universe. The end of the electro-weak epoch. As the W and Z bosons rapidly decayed and the temperature continued to drop, quarks and gluons began to dominate, leading to a new chapter, the quark epoch, a time when fundamental particles collided, interacted, and began forming the building blocks of protons and neutrons. From a blazing sea of energy, the universe's first tiny particles emerged, the seeds of all matter we know today. Time. From 10 to 12 to 10 to 6 seconds after the Big Bang. During this period, the universe continued to expand and cool, but it was still unimaginably hot, around 1 trillion degrees Kelvin. At this point, all fundamental forces had fully separated, and various particles had begun to take on individual mass thanks to their interaction with the Higgs field from the previous epoch. Key particles. Appearing at this stage, quarks, the fundamental building blocks of protons and neutrons. Antiquarks, symmetrical counterparts with opposite charges. Gluons, the carriers of the strong force which glue quarks together. The entire universe was now a super-dense plasma soup filled with quarks and antiquarks, gluons, the binding agent for quarks. Photons, leptons, such as electrons, neutrinos, positrons. These particles collided, decayed, were created, and annihilated in a high-energy dance of chaos. Yet beneath that chaos lay the strict rules of quantum physics. The system reached a state of dynamic equilibrium. Matter and antimatter existed in nearly perfect symmetry. The big mystery: why does matter still exist? If matter and antimatter had annihilated each other perfectly, the universe today would be empty. But for reasons not yet fully understood, there was a tiny asymmetry. For every billion particles of antimatter that were annihilated, one particle of matter survived. These survivors became the foundation of all matter in the universe today. Many physicists believe this imbalance was caused by the weak nuclear force CP violation, a slight preference in how particles decay compared to their antiparticles. As the temperature continued to drop, quarks began to bind together, forming hadrons, specifically protons, neutrons, and their corresponding antiparticles. This marked the end of the quark epoch and the beginning of the hadron epoch, where particles became more stable and matter started to feel real. As the crashing particles settled, a new universe began to take shape. No longer just energy, but real matter. Time. From 10 to 6 seconds to around 1,000 seconds after the Big Bang. After quarks bonded into protons and neutrons, the universe entered a phase where particles began to take on structure and stability. This was the era of hadrons, protons, neutrons, and their antiparticles, leptons, electrons, neutrinos, positrons, and most importantly, the first steps toward atoms. Hadron versus antihadron, the Great Annihilation. As protons and neutrons formed, a large number of antiparticles emerged as well. These particles and antiparticles collided and annihilated each other, releasing energy as photons. However, as mentioned before, a tiny matter-antimatter asymmetry allowed some matter to survive, and thanks to that, the universe exists today. From 1 to 10, seconds after the Big Bang. As the universe continued to cool, leptons like electrons, positrons, and neutrinos dominated. A massive number of neutrinos were released from the plasma, forming the neutrino background radiation, similar to the photon background, but still unobserved directly. Electrons and positrons also annihilated each other, but a small surplus of electrons survived. These would later orbit protons to form atoms. From 10 seconds to about 20 minutes, birth of the first nuclei. At this stage, the universe's temperature and density were just right for protons and neutrons to combine into light atomic nuclei, such as deuterium, 2H, helium-3 and helium-4, 3He, 4He, lithium-7, 7Uli. This era is called Big Bang nucleosynthesis, BBN, one of the best supported events in the Big Bang model, with clear observational evidence. But stability didn't come instantly. Even after nucleosynthesis, the universe was still flooded with high-energy photons. These photons kept colliding with the new nuclei, breaking them apart, a process called photodisintegration. Only when the universe cooled enough did these destructive reactions slow down, allowing the nuclei to survive stably. By the end of this era, the universe had the first stable atomic nuclei, surplus electrons, still not bound into atoms, a massive number of photons, unable to escape because they were constantly scattered by charged particles. All of this was building up to one final phase before light could finally break free, the era of recombination. 380,000 years after the Big Bang, light was finally able to break free from matter. And from that moment on, the observable history of humanity officially began. Time. Around 380,000 years after the Big Bang. After hundreds of thousands of years, the universe had cooled to about 3,000 Kelvin, a low enough temperature for electrons to combine with protons, forming the first neutral hydrogen atoms. This process is known as recombination. What happened during this era? Before recombination, photons were constantly scattered by free electrons. The universe was opaque. After recombination, no more free charged particles. Photons were no longer blocked and could travel freely. For the first time in history, light could move unimpeded across space, and the very photons released at that moment still exist today as the cosmic microwave background, CMB. The CMB, a snapshot of the baby universe. The CMB is a snapshot of the universe when it was just 380,000 years old. It appears as a uniform glow of light from all directions, with a temperature of about 2.725 Kelvin. It is the oldest image humanity has ever observed, and the outermost boundary of current astronomical observation. The Dark Ages. Right after photons escaped, the universe entered a long, quiet phase called the Dark Ages. No stars yet, no light, just cold hydrogen gas drifting silently in the dark. The universe remained this way, until the first stars ignited, ushering in a new age, the era of ionization and the birth of galaxies. From 0 seconds to 380,000 years, the foundations of everything. During its first 380,000 years, the universe went through a series of fundamental physical transitions, formed the first particles, atoms, forces, and light, created the initial conditions for stars, planets, and eventually, life. Everything we know today started in those early, chaotic, miraculous moments. And that's what happened in the first 380,000 years of the universe. A journey from nothing to light, from chaos to order, from uncertainty to the foundation of everything that exists today. What do you think is the most awe-inspiring part of the universe's early history? Do you believe we'll ever understand the full depth of the past? Or will there always be dark corners beyond our reach? Drop your thoughts in the comments below. I'd love to hear your perspective. If you found this video insightful and want to keep exploring the mysteries of the cosmos with me, don't forget to subscribe, hit the notification bell, and never miss the next chapter in our cosmic journey. Thank you for staying with me until the end. See you again among the stars.